You are here at the beautiful University of Lincoln Rise Home campus. We've had a few technical issues and we've sorted that now. So hopefully you're seeing a beautiful live stream on a beautiful sunny day with someone wearing a jumper. But as we get past that, that will be absolutely fine. So you can see a beautiful strawberry farm sort of behind us. And what we do here is we use robots in agriculture. And we're really excited to show you two aspects of the robotics that we do. One is around sort of helping pickers and the hardware elements, and another is around the cognitive services. So I'm going to introduce the team. So Stephen's taking the video. Shout hi.
Hi.
Yes, there's Stephen. Fantastic. Pickers, say hi. Great, fantastic. We've got Catherine and Necro taking second part. Awesome. And we've got fantastic Rupika behind us. Amazing. So fantastic. So we're going to give you a really fantastic rundown of this amazing Thorvald machine. Rupika's going to be doing that. So without further ado, I'll introduce you to Rupika.
Hello everybody, my name is Rupika and I'm a PhD student here. I'm standing next to the very stylish Thorvald robot. Thorvald here is the closest thing I've had to a pet pony. You can see Thorvald has its very own computer, and then it has LiDAR sensors on every other corner, and this is what helps it sense and avoid obstacles. You can see there's a joystick here, which means we can control Thorvald manually, but we wouldn't be needing that today because Thorvald has become smart enough to move on its own. The functionality that we will be demonstrating now is Thorvald can act as a transportation robot, and so when a fruit picker is in need of a robot or a trolley to load their tray which they've been picking, they can call for the Thorvald. Thorvald can go there and pick it up for them. Let's see how it works. Guys, are you ready? It happens sometimes. Thorvald can be a bit injured. Is everything all right?
Hello, I'm about to move. Be careful.
Good, here we go. Things is broken. So as you can see, Thorvald is very, very robust because the agricultural terrain is not going to be smooth at any point, arable or a polytunnel environment. The wheels are very sturdy. The robot carefully plans its path to avoid other robots or even potentially other human beings, and carefully navigate, avoiding hitting on the poles. You can see it repositions itself every now and then to avoid hitting on the poles.
I can leave in 49 seconds. Please load trays.
Guys, can you quickly tell us how you've called the robot to you?
Yeah, it's just an app. I click this button to make the robot come here. So now we are going to load the crate. I'm going to click the same button to send it off.
That's brilliant. Thank you.
Hello, I'm about to move. Be careful.
You can see how simple that was. The user interface is very straightforward, can be used by any picker, even if they don't really know the language. It's pretty simple to use, is what I'm trying to say. You would have observed that the Thorvald mentions that it's going to wait there for 45 seconds. This basically means that if there has been an erroneous call or if it's been called by mistake by the picker, it doesn't continue standing there. It knows it has to come back and not, maybe block the road for other robots or pickers to be traveling. So if the tray is not loaded and if there's no button pressed after it's gone near the picker, it leaves anyway after 45 seconds, being the diva that Thorvald is. Do we have any questions? None as of yet. Okay. We can now move on to Nico and Catherine, who have something very interesting on their own.
Hi everyone, I'm Catherine.
And I'm Nika, and we are also PhD students here at the University of Lincoln.
And today we're going to be showing you the basics of a fruit counting system. So as Gary mentioned, today we have a beautiful sunny day here at Rise Home. What this means for the crop is that today the crop's going to ripen really fast, but this is always impacted by the weather. So farmers, when they are trying to schedule their labor or trying to determine if they're going to be meeting their market requirements, have to do some sort of yield forecasting. They have to work out how much fruit they're going to have and when they're going to have that fruit. Now, to be able to do this, they need to have a good idea of A, what the weather's going to be doing, but also what the crop is doing at the moment. So here you can see we've got some unripe strawberries and some semi-ripe strawberries. But anyway, to do this yield forecasting, you have to have an idea of the fruit counts. To do this manually would be very difficult. This is a very, very small strawberry farm. On a commercial farm, impossible to do it manually. So what we're going to show you today is the basics for a robotic system to do just that. Let me introduce you to our Thorvald. So this is another Thorvald robot, cousin of the one you met before. And what this Thorvald is doing is it's going along and taking a live stream of the crop, which will later be uploaded to a database. The Thorvald has some special cameras, which have got both RGB, which is like your phone camera, but also depth, which shows you the distance away of the berry, which is important for reasons Nico will mention. We're going to switch across to the video feed from last year now.
All right, thank you, Kat.
I mentioned we have a video here from last year, and that's because we're a bit too early in the season, so we don't have a lot of fruit right now. But we've collected this video in much the same way that we're collecting data right now last year. And as you can see, we have a lot of strawberries in this image feed. And after collecting this video, we are uploading it to one of our online databases in the cloud. And after doing that, we run our algorithms, which are in this particular case a neural network, so a sort of machine learning algorithm. And we run that on top of the video data. And what that does, it is detects the strawberries. So it localizes them in the video feed, as you can see here on the left-hand side in the image. And it will also detect whether we are dealing with a ripe strawberry and not yet ripe strawberry, strawberry flower, things like that. And as Catherine has already mentioned, all of this is very important to perform labor scheduling, yield forecasting, and stuff like that. Cool. So back to Catherine.
So as you've seen, a system like this is really suited to overcoming that problem where the manual count isn't possible, but with robotics and some sort of artificial intelligence, this makes a really good solution. And the basics of fruit counting, fruit detection, this is the basis of a lot broader applications. So super, thank you. And are there any questions?
Okay, we've got one question. What is the most challenging aspect of the project?
So one challenge in this project is that you don't want to count the same berry multiple times. So as the robot moves down the road taking the video of the live stream, it will take sort of like a picture, because that's what a video is really. But if you run your detection algorithm on that raw, you will detect the same berry many, many times, which will give you absolute nonsense when it comes to counting. So you need to keep track of which berry is which. And so there's this tracking component which is involved, and I'd say that's probably one of the more complicated parts of it. In the demo that Nico showed you, on the right-hand side, there was some white depth cloud, which is using that second camera that I mentioned, and there were little red dots, and what those red dots were indicating was which berry was which in the moving frame. Any more questions?
Hi everyone, my name's Gary Clausen. Welcome to the second edition of Agri-Food Robotics. We had a wonderful first session and we're really excited to show you the second session if you didn't happen to capture that. We are here at the University of Lincoln, beautiful Rise Home campus. You can see behind me, we've got our beautiful strawberry farm, and this is where we do a large part of our agri-food robotics. I'm going to introduce you to the amazing team. We've got Stephen on the video. Say hi, Stephen.
Hello, everyone.
Fantastic, thank you very much. We've got our pickers down the back there. Say hi, guys. Fantastic. We've got Catherine and Nico who are going to take us through the second segment. And we've got the amazing Rupika behind us who's going to introduce us to our initial robot. So, well, thanks again for tuning in. So what do we do here? Well, we're focused on robots in agriculture. There's a lot of opportunity that these robots can provide. And here we're going to demonstrate two items. We've got a robot behind us who's going to augment the help of the pickers, and it's going to do a lot of the labouring work for them, but it does this in an autonomous way. So Rupik's going to take you through that. Catherine and Nico are going to take you through a cognitive element where we're going to see how do we know when to pick strawberries and how does a machine like to look at them. So without ado, I'll introduce you to Rupika and we can go through this process. Thank you.
Hello, everybody. My name is Rupika, and I'm a PhD student here. I'm standing next to the very stylish Towel robot. Towel robot is the closest thing I've had to a pet pony. Towel here has its own computer, and then you can see it has a LiDAR on every other corner. So this is what helps it sense and then avoid obstacles. You can see we have a joystick here, which means we can control Towel manually, but we are not going to be doing that today because Towel has become smart enough to do things on its own. Today, we are going to be demonstrating how Towel acts as a transportation robot to aid fruit pickers after they've collected picking one tray of strawberries or so. Are we ready, guys? Brilliant.
Hello, I am about to move. Be careful.
Towel by Saga Robotics is a very, very robust robot. You can see the terrain in an agricultural domain is not always smooth. It's pretty crude. The wheels are very sturdy. Towel carefully positions itself in such a way that it avoids other robots and potentially even other human beings and navigates, avoiding hitting on any poles. You can see it repositions itself every now and then it makes its way through the picture.
I will leave in 49 seconds. Please load trays.
Can you quickly tell us how the robot has come to you now? What have you done?
It's just an app. Like I click a button to make it stand here. Like I'm going to load a tray now. It's time to send it back. I'm just clicking a button again.
Hello, I am about to move.
Brilliant, thank you. As you just saw, the calling of a Towel robot is very, very straightforward, very simple. Doesn't need the picker to be, technically educated or anything. Even language barriers aren't usually a problem. The user phase is very, very simple. You would have noticed that the Towel mentioned itself that it's going to be staying next to the picker for 45 seconds. That it will leave in 45 seconds. The reason that it says this is because in case the call was an erroneous one, if somebody pressed pressed to call for a robot by mistake, then the Towel does not waste its time or even block the path for other robots or human beings to pass through. Instead, if there is no tray placed on it within 45 seconds, it comes back anyway. It does not wait for anybody. Towel is being a diva. That's what it's meant to be. Do we have any questions?
So we've got one question.
Mm-hmm.
How does the mapping work?
Oh, that's a good one. So the mapping for most of the research done with Towel robots are discrete, like they are on a topological level. So the polytunnel environment, if you can just show them the polytunnel environment once. So this is discretized into hypothetical nodes, like virtual nodes. So the entire farm is mapped as hundreds of different nodes And so the input, like on a very, very simple level, the input given to the robot is the number on the node that it has to go to. For example, this picker, the position that he is standing in might be a particular node, say node 60. So the app basically tells the robot not the exact position, but approximates it to the node, and then it quickly traverses to the node. The path planning is discrete. It's on a topological level. Is that it? Brilliant. We will now move over to Catherine and Nico, who have something very interesting to share.
Hi everyone, I'm Catherine,
And I'm Nika, and we're also PhD students here at the University of Lincoln.
and today we're going to show you the basics of a fruit counting system. So as Gary already mentioned, today we have a lovely, bright, warm, sunny day at Rhizome. And what this means is that today the fruit will be ripening really fast. Now this poses a problem for farmers because farmers need to have an idea when their fruit will ripen and what sort of volumes of fruit they can expect to have ripe at any point in time. And this is important because they need to know how much labor to schedule and also whether they're going to meet their market requirements. So if it's going to be enough or too little. So to do this, they need to have some form of yield forecasting system, which takes into account sort of the weather, but also very, very importantly, what the crop is currently doing. So as you can see, we've got some unripe strawberries and some semi-ripe strawberries. And to get an idea of what sort of yields you can expect, you really need to be able to count the berries to do this accurately. Now, as I'm sure you can imagine, this is just a small strawberry farm. And even here, this task is daunting, to be able to count every single strawberry on the crop, to be able to make an accurate forecast. And on a commercial farm, this would simply be impossible because you'd have thousands and thousands of plants. And so as a result, what we're going to show you today is the basics of a robotic system, which is trying to do just that, count fruit. So let me introduce you to our Thorvald. So this Thorvald is the cousin of the one that you've just met. And what this one is doing is it's got some cameras. These cameras are quite special. There's an RGB camera, which is just like the one on your phone. There's also a depth camera, which shows you how far away in the picture an object is. And what this robot does is it collects a video feed, which is uploaded to our database, and we can then run some artificial intelligence and analytics on that afterwards. So across to Nico to show you just that.
Here is a video from last year, because right now it's just a tad too early in the season for us to actually have a lot of ripe strawberries. So we collected this video much in the same way that we're collecting data right now, last season. And we uploaded the video to one of our online databases, where we then ran our algorithms, which in this particular case is a neural network, a sort of machine learning algorithm, in order to perform detection for the strawberries on this video feed. So basically that means we ran the neural network on it in order to localize the strawberries and to detect with what kind of strawberry we are dealing. So whether it's a ripe strawberry, an unripe strawberry, or a strawberry flower, for example. And as Catherine has already mentioned, this is quite important for labor scheduling, yield forecasting, stuff like that.
Super. So as you can see, a system like this is really beneficial. Fruit detection is the basis of fruit counting. We can also build fruit tracking on top of that. And this would allow us to count the fruit on a strawberry farm. And that in turn would allow for decision support to assist the farmers. So thank you.
Are there any questions?
Okay, so we've got one question from sorry, I might butcher this, Manal Hilal. Do these robots report diseases in their crops and send alarms?
So that's not something which is implemented in this particular system, but it's something which the current system could very easily be adapted to include. Basically, when you build a system like this, you start off by collecting a data set. And what that means is you take some pictures and then you annotate it. So you draw sort of boxes around this is a ripe fruit, this is a semi-ripe fruit, this is an unripe fruit, this is a flower. But you could also add another category to that, which is this fruit is diseased. And so simply by adding another category, you could extend this system to potentially be a diseased fruit counting system and that could then be attached to something like a warning.
What we are already doing, however, is we are treating for mildew with a UVC treatment system that is attached to a different thought robot. That's just going through the rows at night, and it treats the plant with a UVC lamp in order to ward off mildew.
And that's run by Saga Robotics. Any more questions?
Okay, so we have another question actually. What is the most challenging aspect of the project?
So one of the challenging aspects of the project is the fact that you don't want to count the same berry multiple times. So as the robot moves down the row, it collects this video, and a video is basically a series of images, and the detection system will be run on each of those images. So you don't want to count the same berry in sort of 25,000 frames, because then you would have the same berry counted 25,000 times. And so you need to really keep track of which berry is which. And so in the video that Nico showed, the demo that Nico showed, on the right-hand side, there was sort of some white depth cloud with red dots on it, and that was the tracking system. So that was keeping track of which berry was which in the image. I'd say that's a challenging part of the whole process.
Any further questions?
Okay, we've got no more questions. We're actually running out of time now, so.
Super. Thank you.
Super. Thanks for joining us.
Hi everyone, my name's Gary Clausen. Welcome to the third instalment of Agri-Food Robotics. It's a beautiful sunny day here at the University of Lincoln, beautiful Rise Home campus. You're joined at the wonderful strawberry farm, and we're going to be showing you loads of cool stuff around agri-food robots. First of all, I'd like to introduce the team. So say hi, Stephen, who's on the camera.
Hello, everyone.
Hello, fantastic. We've got two pickers down at the bottom, Sam and Stuart. Fantastic. We've got Catherine and Nico, who are going to be taking the second segment. And we've got the fantastic Rupika, who's going to be taking us through robotics in the first instance. So, what do we do here? Well, we are a live farm dedicated to agri-food and how robotics will work in agriculture. And we've got two demonstrations to show you today. We've got a fantastic augmented support for pickers demonstration. So this is where the pickers will need, for fresh strawberries, which we can see in the back, will need support around any of the labouring elements. So this really helps them when rather than having to carry lots of baskets around. And we've got a cognitive element as well. So you may be asking yourselves, what does a strawberry look like to a robot? How can a robot see a ripe strawberry, and how does it then react to that particular thing? And that's what Catherine and Nico are going to take you through. So I'm going to introduce you to Rupika, and Rupika's going to show you this fantastic demonstration. Rupika.
Thank you, Gary. Hello, everyone. My name is Rupika Ravikana, and I'm a PhD student here. I am standing next to the very stylish Toggle robot. Toggle robot here is the closest thing I've had to a pet pony. So you can see Toggle has its own computer, and then there is a LiDAR for sensing in every other corner. So it uses LiDAR to sense and avoid obstacles. You can also see we have a joystick, which means we can also control Toggle manually. We are not going to be doing that today because Toggle has become smart enough to move on its own. The demo now is going to be on how Toggle can act as a transportation robot to help with pickers after they have finished picking a tray of strawberries. Are we ready, guys?
Hello, I'm the host. Be careful.
So, Toggle by Saga Robotics is a very, very robust robot. The agricultural terrain is not smooth. Arable farming or a polyton environment such as this. The ground is always pretty smooth. You can see how the Toggle carefully navigates itself, avoid other robots and potentially even other human beings. It repositions itself constantly to avoid feeding on the poles. You can see right there.
I believe in 49 seconds. Please load trays.
Can you quickly tell us how the robot has now come to you?
Yeah, it's just a simple app. I use the button to bring it here. That's it. Let me load the tray. Now I'm going to send it back again by clicking the button.
I will leave in 49 seconds. Please load trays.
Brilliant, thank you.
I'm about to move. Be careful.
So as you just observed, it is very, very straightforward. Oops, we had a little confusion, right? So it's very straightforward to call for a Toggle robot. The user interface is very simple. The picker need not be technically educated, or even language barrier is not usually a problem. You would have noticed Toggle said that it would wait there for 45 seconds before being back. This is only because in case the call was an erroneous one, in case the picker pressed on the call button by mistake or something, then Toggle would not endlessly keep waiting there for it to go back, because it will understand that it's been called in by mistake and make its way back without being a hindrance for anybody to pass through the path. So Toggle is a diva because it does not wait for anybody. Do we have any questions?
So we have one question. What's the future work in transportation robots?
Very interesting. So I myself researched a little bit into that. So now we saw the pickers manually calling for the robot, and the position that they are there is then transmitted to Towel and then plans its path and goes. But what we are trying to, a set of us are trying to do, is to automate this entire thing, make it intelligent. For example, if there are a number of pickers in a real farm, there are hundreds of rows, many more pickers than just one or two. So depending on where the pickers are and how they move about, and studying the human behavioral models, we aim for the transportation robots to understand when and where they have to be without having the picker call for them. So that's the potential future work. Okay, I think that's it. Yeah, is that it, the questions?
Well, we've got one more question, a bit short on time, but how many strawberries can the robot carry at once?
Oh, okay, so interesting one. The robot can carry up to 3 loaded trays. So one loaded tray usually has 10 boxes of strawberries. So one box of strawberry is around 500 grams. So 2.5 kilos of strawberry per tray, 3 trays. That's what it can carry currently. Do we have any more questions?
We do have another question.
Oh, go for
We're a
it.
bit short on time.
Go for it.
What is the biggest challenge in front of you?
Oh, the biggest challenge. I think the biggest challenge is data collection of pickers, because as we are trying to make the system more intelligent, use behavioral models or even deep learning or so, we struggle to collect data, especially that of the pickers, because that is not for example, if for people who are doing vision, when we have to observe the data from strawberries, then you can have a farm of strawberries and then just go for it and observe. But then when we want to understand the realistic behavior of pickers, it's not that easy, because they have to consent to being captured, and then we have to have some methods so that they don't behave or act differently when they are being recorded as opposed to how they would otherwise act. So the challenge mainly lies in collecting data. We don't really have a huge repository of picker behavior data. That is what I would think the biggest challenge is. Do we have any more? All right. If there are more questions, we always have the next time. We will now move over to Catherine and Nico.
Hi everyone, I'm Catherine.
And I'm Nico, and we're also PhD students here at the University of Lincoln.
And today we're going to be showing you the basics of a fruit counting system. So as Gary already mentioned, today is a lovely warm sunny day here at Rise Home, and this will impact how quickly the strawberries ripen on the crop. Now that's really important for the farmers, because they need to know when to schedule their labour to come and pick ripe fruit, and also what volumes of ripe fruit they're going to get. And the weather obviously impacts that. However, something else that's really important is that the number of berries is also going to impact, obviously, the number of unripe berries at the moment will impact how much ripe fruit we will have in a few weeks' time. And this process of knowing how much fruit you're going to have in the future is a process called yield forecasting. Now, for yield forecasting, it's really important to have an idea of the volume of fruit that you have at the moment. And how you would answer that question, well, manually counting this would be fairly impossible. On a small farm like Rise Home, you might just manage it, but on a commercial farm, that would be absolutely impossible. And so what we're going to show you today is the basics of a fruit counting system. So let me introduce you to our Thorvald. So this Thorvald is the cousin of the one you met before. It uses the same navigation type systems, etc. What it does is it's got these special cameras which have but also depth cameras, so RGB and depth. And it collects a video feed, and that video feed will later be uploaded to our database so that we can then perform some analytics on it. So over to Nico to show you that.
Thank you, Catherine. So, as Catherine has already just explained, we are collecting some video samples here, but we are currently a bit too early in the season for there to actually be enough ripe fruit for us to perform a fruit counting system. So what we have here is a video from last season, which we collected just in the same way that we're collecting data right now. And as you can see, there are plenty of strawberries in the video stream here. And the way that we collect these data is that we film these strawberries on the farm with the Thorvald robot, and then we upload the video to the cloud, to one of our online databases. And then we run our algorithms on it. So these algorithms include a neural network, a sort of machine learning algorithm, which detects the strawberries in the video feed. So it localizes them, and it detects whether it's a ripe strawberry, an unripe strawberry, whether it's a strawberry flower. As Catherine has already mentioned, all this information is very important for yield forecasting and labor scheduling by predicting when the strawberry is going to be ripe and how many strawberries are going to be ripe at which point in time.
Super. So as you've seen, a system like this is really beneficial because these AI-based solutions allow us to gain much more insight into the crop. We get a far more granular level of data than we would otherwise be able to have. And that really, really improves the potential for the decision support such as these yield forecasting systems. So yeah, fantastic. I'm not sure if there are any questions.
Okay, so we've got one question here. Can the robots detect diseases in the plants?
So at the moment, the current system can't do that, but it would be really quite straightforward to adapt it so that it could. So how the system works at the moment, to build a system like this, we would collect a data set. So a data set would involve taking video or such along these rows and annotating it. So annotating it means we would manually go and draw like a box around each of the different classes of fruit. So a ripe one, an unripe one, a semi-ripe one, a flower, etc. So at the moment, it's just those categories. But if we were to add another category for disease, it would then be able to count the diseased fruit as well.
And we are also currently using the robot in part to treat diseases like mildew already by treating the plants at night with UVC light, which kills off the mildew. So while it cannot yet fully detect it, but it helps us support battling disease already.
So that's a system that's been developed by Saga Robotics. Any more questions?
Okay, we've got another question. What happens if the robot loses track of the strawberry?
So that does happen from time to time. So all these models that we work with have a sort of a confidence interval of how well they work. So we train them up to a level where we're satisfied that the error margin would be not too bad or workable, acceptable in the industry. And then if it loses track of a berry, ultimately what might happen is it would get counted twice, but that would fall within the error margin of the model, so it would still be deemed acceptable.
Any further questions?
Okay, so I've got a question. Why do you guys use the RGBD camera?
Nico, do you want to take this one?
Sure. So we use an RGBD camera, with the RGB camera just being a camera, as Catherine has already explained, like the camera on your phone, just taking regular pictures. We also use a D, which is the depth component, which tells us how far away objects in the image are. And we use this to be able to localize strawberries in 3D space, which helps us in tracking and in applications like automated fruit picking, which we're working on at the moment, basically to get a full 3D representation like humans have already of the surroundings.
How much time do we have left?
12.
So I can expand on that slightly. So if we were to consider that you took a photo of me like this, if I drew a square like this on a picture, you wouldn't know how close it was to my face. But if I drew in 3D with the depth, you can then tell if that square is here or if that square is here. So that's why it's useful in 3D space. Thank you.
Hello everyone, my name's Gary Clausen and welcome to the University of Lincoln beautiful Rise Home campus and joining us for our agri-food robotics talk. So you are here amongst friends. We have Stephen on the camera. Say hi, Stephen.
Hey everyone.
And we've got two pickers down here. Samasuri, say hi. Hi. Yeah, fantastic. Catherine and Nico are going to take us through the second session. And the amazing Rupika behind us who's going to be talking us through the robots in a moment. But first, what do we do here? So we're a soft fruit farm, but we do broad things around that as well. But mainly we focus on robotics in agriculture and how we can help from the cognitive side and how we can help from the labour side as well. So it's crying out for this type of support now, and robots are a perfect augmented tools to support that. So we've got two demonstrations to show you. We've got one where we're going to help the pickers with their physical loading of strawberries, so they don't have to keep walking around everywhere. And we've got a cognitive sense as well, where we're going to see how the strawberries are seen, what a robot thinks a strawberry is, how it perceives it, and once it's done that, what it actually does with it and why it's useful. So without me going on, let me introduce you to the amazing Rupika. Take us through the robot.
Thank you very much, Gary. My name is Rupika Ravikhanna and I'm a PhD student here. I'm standing next to the very stylish Tobble robot. Tobble robot is the closest thing I've had to a pet pony, and I'm hoping I can piggyback on it and get a ride back home. That's not in the demo, for another day. So the Tobble robot has its own computer, and then it has a LiDAR for sensing in every other corner. You can see that we have a joystick, which means it can be controlled manually, but we don't need it today. We're not going to be using it today because Tobble has become smart enough to move about on its own. Today, the demo is about how Tobble acts as a transportation robot to assist pickers to pick up their trays after they've picked one tray of strawberries and come back and unload them. We are going to now see how that works. Are you guys ready?
Hello, I am
The Tobble robot by Saga Robotics is extremely robust, especially because it works in the agricultural domain. The wheels, as you can see, are pretty sturdy. The robot now carefully navigates, avoiding other robots and other people potentially, and repositions itself so as to avoid hitting the poles, and moves to its target destination, which is the pickers.
I believe in 49 seconds. Please load trays.
Can you guys quickly tell me how you've called the robot?
Yeah, we have a simple, cool app. Like I used a button click to bring it here. That's it. So it's time to load the trays. So it's again a button click to send it back.
Oh, that's brilliant. Thank you.
Hello, I am about to move. Be careful.
So as you just saw, the user interface for calling a robot is very straightforward. It usually, the language barriers are easily overcome because there are just two commands. The picker need not be technically educated to handle this. And also the interesting part is you would have heard the Tobble say that it's going to stay there for 45 seconds. This is because if the call has been erroneous, if the picker has pressed on the button by mistake, then Tobble will not waste its time and be a hindrance to other robots or other pickers who want to use the path for traveling across. It'll understand that it's been called by mistake or whatever, and it just leaves anyway. So that's that's the kind of the little intelligence I think a part of which was demonstrated in the demo right now. So Tobble is a diva, doesn't wait for anybody. Do we have any questions?
Okay, we have one question. How does the robot know where it is?
Very, very interesting one. Come over here, Stephen. So you see the LiDAR over here. So there's another similar one in the other corner. So the robot does a 2D scan of a laser scan of the area around it. So it's a one-line single scan. And from that scan, it recognizes the corners, obstacles, and the buildings around it. So it makes a guess of where it is in comparison to the truth map that it already has. And as it moves and as it captures a few more images out of its laser scan, it confirms of where it can be. It eliminates possible options that it can't be, and then finally makes a very informed guess of where it probably is. Are there any more questions? They're not. All right, thank you very much. We will now move on to Catherine and Nico. So that's a bye from me.
Hi everyone, I'm Catherine.
And I'm Nico, and we are also PhD students here at the University of Lincoln.
And today we will be demonstrating the basics of a fruit counting system for you. So as Gary has already mentioned, today is a lovely, bright and sunny day at the University of Lincoln. And what this means for our crop is that the strawberries will ripen quite quickly. Now the weather is obviously really variable, and this poses a huge problem for farmers because they don't really know what yield to expect and when. Now a good way of trying to work this out is to have a look at what your crop is actually doing. So having a look at how many unripe berries, partially ripe or currently ripe berries you have, and how many flowers are coming. But to manually go down one of these rows and count the berries, or across an entire small farm like this, or even, impossible, a commercial farm where there are thousands and thousands of berries, that's just not possible. And so a manual count isn't feasible. And a robotic system, like what we're going to show you today, is potentially the solution. So let me introduce you to our Thorvald. So this Thorvald is the cousin of the one you met just now, and this one has some RGBD cameras on it. That means that they've got regular cameras like you have in your cell phone, but also a depth camera, which shows how far away in the image all the objects are. And this video feed, which is collected by our robot, is then later uploaded to our database, and we can then run some analytics on it. So over to Nico to show you that.
Cool. Thank you, Catherine. So as Catherine just mentioned, we are collecting a video feed from the cameras on the Thorvald robot, and the video that you see here on my screen is a video that we collected last year because right now it's just a tad too early in the season for us to have enough ripe fruit for us to perform any actual strawberry counting. But the data has been collected last season in exactly the same way that we are collecting data right now. So we just sent the Thorvald robot through the strawberry farm to collect the data. It will then upload the videos to the cloud, to one of our online databases, and this is where we then run our algorithms. In this case, the neural network, a sort of machine learning algorithm on top of the data. And what this does is performs strawberry detection on the video feed. So it locates the strawberries in the video, and it tells us whether it's a ripe strawberry, an unripe strawberry, or strawberry flower, which is quite essential for performing yield forecasting or labor scheduling for picking and stuff like that, as Catherine already mentioned previously. Right, so this is basically how we do strawberry detection, and yeah, that's really the gist of it. Back to Catherine.
Super. So as you've seen, a robotic system like this, coupled with machine vision technology, is really suited to these tasks which are impossible to perform manually, and thus provide vast amounts of data which can provide decision support to our farmers. So thank you very much. Are there any questions?
Okay, we've got one question here. How do real-world conditions impact the system?
So this particular system has been developed specifically for real-world conditions. And the reason real-world conditions are a problem is obviously because we are outside, there is sunlight on some days, and some days there is clouds, and some days there is rain, and that makes the images look quite different. But because our data has been collected in real-world conditions on real-world data, and trained using a machine learning algorithm, so a convolutional neural network, this type of algorithm is quite robust to learning these sorts of variations within the data You can also augment the data, which means provide some artificial variations, such as adding brightness augmentation, which means just changing the lightness of the image, just try and introduce some more fluctuations so that it learns the true sort of underlying pattern of this is what a ripe strawberry or an unripe strawberry is, and it can then perform accurately. Are there any more questions?
We have another question from A. Javi. How fast can it scan? Wouldn't it need a lot of time to scan a big field?
Well, there are different factors to play into this. On the one hand, we have the speed of the Thorvald robot that goes currently quite slowly along the rows for various reasons, among others safety reasons, because there are pickers in the field and everything. The camera is operated at a frame rate of 30 frames per second at the moment, and the neural network that is run on top of it, it takes, I think, roughly maybe a tenth of a second to infer on a single image. So we are really, at the very least, we are operating at a 10 hertz detection frame rate for the video feed, but the robot could go much faster than it currently does. So while I cannot give you the definitive answer on how long the data collection would take, it could be sped up quite significantly in comparison to what it is now, because you can also deploy multiple robots simultaneously to go through different rows at the same time. So basically, it varies.
Super. Thank you so much for joining us today, and all the best.
Thank you.